Hi again, everyone. So this one was the detection of internal heat damage and the identification of techniques to prevent the expression of the disorder in plums. So the fruit of certain plum cultivars subject to extremely high air temperatures in a week or two before harvest may develop heat damage in different forms. You get external heat damage, and that's typically caused by direct sunlight. It's easily identified by discoloration, sunken area of the surface or the skin. That's almost what I call the sun pitting that you get. And then usually visible on the fruit at packing and can therefore be removed from the commercial consignment. Then you get the internal heat damage. It's difficult to identify since it's not visible at harvest. It's not visible at harvest, you can't see it. It's reportedly caused by high ambient temperatures rather than direct sunlight, but the exact cause of the mechanism is uncertain. And then the fruit pulp temperatures escalates higher than the ambient air that we saw earlier in one of my other talks, resulting in damage of the cells. And that is expressed as internal browning in that picture of that Letitia. So the objective was to develop a risk assessment method to establish the likelihood of internal heat damage on the fruit prior to export, and to confirm if slow cooling of Letitia plums after harvest would reduce the internal heat damage compared to rapid cooling. And that was done by Ari de Kock previously, Kumala and Davids and Murray Hahn in 2006. An additional requirement was to ascertain the effect of 1 MCP in combination with cooling rate manipulation on plum fruit quality after cold storage. So the part one was to develop a risk assessment method. Maturity indexing was conducted in each population. The temperature method tested is to force development of the internal heat damage in this susceptible Letitia plums to enable a risk assessment. And that we did was, there were 4 treatments that we did. We did a 24-hour forced air cooling, followed by 2 days holding period at minus 0.5 after that forced air cooling. And then we had in each of those ones we had a evaluation directly after that holding period. And then the other treatment 2, we had a 2-day ripening or at 20 degrees. And then treatment 3 and 4, we also forced air cooled at 6 hours. Holding it for 3 days at minus 0.5, and then also each one had a 0 or a 2-day at that ripening period. The part 2 of this trial was to see the effect of those forced air cooling, the 24 hours, the 48, 72, and then we also included that 6 hours that we did in that risk assessment. And all 3 of the 24-hour, 48 hours, and 72 hours had a plus and minus 1 MCP, and you can see the cooling rates that we tested there. If we look at that risk assessment, at part 1, we could clearly see that the internal heat damage was significantly better after that 2 days ripening process at 20 degrees. And it was significantly higher than cutting directly after the cooling. That's only at 6%. If we look at the difference between the 6 hours and the 24 hours cooling, you can clearly see that the 6 hours had 14% internal heat damage compared to the 5.3% of 24 hours. So your period of forced air cooling also plays a role there. And then in 2021, we could see that the combination of 6 hours and the 2 days at 20 degrees Celsius gives you an indication of the internal disorders and the possibility of internal heat damage, where if you didn't use that 2 days at 20 degrees, you didn't see any disorders popping out in that 6-day period. And that is an example of that risk assessment protocol that we developed with the 6 hours forced air cooling plus the 3 days at -0.5 and then the 2 days at 20 degrees C. We can actually induce that disorder, what you will get on the other side, but you can actually see it before you send it. This is just the effect of the, this is now the second part, where we actually check the effect of the cooling rates on the effect of the expression of the disorders. Like I said, this was done on Letitia's, and we can clearly see that the 24 hours cooling had less shrivel, but it had high internal heat damage. So that's where you have to play basically off the two. What is worse and how can you make it work for you? If you look at that 6 hours 1 MCP, you can see that there's 23%. So it's clearly visible that if you force air cool too fast, you will induce more internal heat damage, where compared to if you only force air cool for 48 or 72 hours. I'm going to quickly go through this. Yeah, so you can clearly see that the 48 hours with 1 MCP gave you the best result with 0% internal heat damage and only a 14% total internal disorder compared to the others that was much higher in the 30s. We had basically the same effect after at the 2021 season. We, however, saw that 48 and 72 hours without the 1 MCP had slightly higher shrivel than the similar forced air cooling with the 1 MCP, and the reason for that is unclear. And there, once again, the 48 hours with 1 MCP and the 72 hours gave the best total, the lowest in total internal disorders, but there was slightly higher shrivel. It's just clear that it was clear that we can actually force the internal disorders with that forced air cooling regime, that Letitia prediction model. And it's only indication. It's not. It doesn't say how many, what the extent of the disorders will be. And yeah, that you would rather use 48 hours forced air cooling compared to 24 hours if you have an option. Yeah, that's basically that in a nutshell. Okay, thank you very much.
Thanks, Handré.
I just want to go.